நான் ஒண்ணும் பண்ணல. நீங்க 85 to 88 சிகரோல இன்பாக்ஸ் ஞாபகம் வருது. 85 3 years இது 6 மாசம் என் கூட பேனர்ல இருந்தீங்க. I remember those days.
ஆமா கரெக்ட்.
ஃபர்ஸ்ட் இன்பாக்ஸ் ஃபர்ஸ்ட் இன்பாக்ஸ் நீங்க உங்களுடைய சப்போர்ட்ல பண்ணோம். கரெக்ட். நானு முனியசாமி பகலோடி ரெகுனேஷன் 4 பேர் பண்ணோம். You are with us. அதுதான் என்னோட லேர்னிங் கர்வ்ல ஆரம்பிச்சோம். இல்ல you taught us உங்களோட இருந்து நல்லா நிறைய கத்துக்கிட்டேன். நீங்க டிசாஸ்டர் பத்தி என்னன்னா நிறைய learned. I was living with you for about 6 months. நல்லா இருந்தது.
இல்ல எக்ஸ்கியூஸ் மீ, யாரோ பேசுறது எக்கோ ஆயிட்டு இருக்கு. யார் பேசுறது எக்கோ ஆயிட்டு கொஞ்சம் பாருங்க.
அப்படியே
there is some echo.
தெரியல எக்கோ எங்கன்னு தெரியலையே.
நைட்டு கொஞ்சம் தூக்கம் இல்ல. ஒரு நேத்திக்கு 100 question we have to create a question bank and give it nowadays for the online examination. I mean Professor Sitaraman knows that. Ramswamy sir knows that. 100 questions in welding processes.
Oh.
And they will jumble it up and then give it to the students. So that exercise I was doing the whole day yesterday. Rashekar.
Yes sir.
Have you informed the NIT people?
Sir, it has been circulated in the joining group. Actually, what we are having for the WhatsApp group for the building, for the whole country, it has been. Yes, sir.
No. Actually, our NIT postgraduate student, our Ananthan had arranged a talk by me on career in welding for those students. I don't know whether any postgraduate student from NIT is here joining us.
Sir, this intimation has gone to all the people in the joining group, which includes NIT professors and others.
இல்ல நீ அனந்தனுக்கு அனுப்பிச்சிரியா இப்போ?
வெல்டிங் குரூப் போயிருக்கு. அனந்தனுக்கு போயிருக்கு. ஜாயினிங் குரூப் அனந்தன்ல இருக்காரு. போயிருக்கு, கண்டிப்பா போயிருக்கு. அனந்தனுக்கு தனியா அனுப்பல, நான் வேணா ஃபார்வர்ட் பண்ணுறேன்.
அனந்தனுக்கு ஃபார்வர்ட் பண்ணிடுங்க. He will take care.
நான் அந்த ஜாயினிங் குரூப் எல்லாத்துக்கும் போட்டிருக்கேன். அதுல வந்து எல்லாருக்கும் நிறைய இண்டஸ்ட்ரீஸ் நிறைய பீப்புள் இருக்காங்க. அதுல கிட்டத்தட்ட ஒரு 500 people are there in that list. அவங்க எல்லாருக்கும் போயிருக்கு ஆக்சுவலா.
Boss, hello.
Oh, வந்துட்டீங்களா?
Boss, what is this? I have to see you online.
Yeah, that's true.
Boss, we are missing you. We are waiting for you.
எங்க இருக்கீங்க? ட்ரிச்சியா சென்னையா?
Trichiera, everything is online.
சரி, டாக்டர் எங்க இருக்காங்க?
Everything is online.
இல்ல டாக்டர் எங்க இருக்காங்க?
டாக்டர் இங்க தான் இருக்காங்க. ஜிஹெச்.
ஓகே.
ஆமா, மேடம் எப்படி இருக்காங்க?
ஃபைன், யா, ஓகே.
என்ன பாஸ் மறந்துட்டீங்களா எங்களா?
எல்லாம் லிட்டில் டயர்ட். ஐ அம் ஃபைன். இன்னைக்கு 2 லெக்சர். क्वेश्चन பேப்பர் போஸ்ட் பண்றது இல்ல.
லெக்சர் வந்து நம்மளுடைய பாஸ்ட் டைம்.
அதெல்லாம் பழைய காலம் பாஸ்.
அப்படியா? என்ன பாஸ்? I still remember your lectures.
Once கேக்குறேன்.
Uh,
Main difference between WRI lectures and academic lectures are,
yeah, that's there.
for example, say one topic, distortion or design. அப்படின்னா, in WRI, we used to talk only 2 hours or 3 hours. Here, the whole course, 45 hours. So you have to expand the topic as per the syllabus. And, it's a very, quite a tiring exercise.
Yeah.
So initially, I did not realize. Before 3-4 years, I realized that it's not so easy to be an academician, especially one topic which we used to talk about 2 to 4 hours, so to expand it 10 times. So that much input you have to prepare, and so that puts a lot of pressure on you.
But you are a wonderful teacher.
Okay, but daily, daily I work between 6 to 10 at home. Thanks to my wife who is busy with her friends apartment. So that gives me 3 hours of working. And the serials. The serial பார்க்காம அவங்களால இருக்க முடியாது. That also helps me quite a lot.
Yeah, we have to thank serial directors. They are making them happy also. Yeah. When you are coming to Trichy next time?
I may come tomorrow. Tomorrow night I am coming.
Okay.
But I am having my mother's ceremony on
Okay.
Sunday.
Okay. Well, we will not disturb you.
I am leaving for Chennai.
Okay.
For my mother-in-law's ceremony.
Oh.
So both are very close.
Okay. Okay.
I am coming back to Coimbatore. I am not staying. But you know that I think I don't know whether Rajshekharan and others know this.
Yeah.
We have started the fabrication. Between Ahmedabad and Mumbai called Bullet Train Project.
Okay. Okay.
So I am a member of this NHSRC,
Okay.
National High Speed Rail Corporation. And L&T has backed the order for 1,500 crores.
Okay.
They have identified 2 firms in Trichy, Toolfab and Velmurugan.
Okay.
So as a part of the committee with NHRC, I am likely to come around August 13, 14, 15.
Okay.
For, starting the mock-up fabrication at their place.
Okay.
So I will be coming to Trichy very often because there are 2 factories who are going to do that.
Yeah.
Some more have opted, but in fact, Rajshekharan, you remember I came to Trichy along with the team. We met ED also.
ED and all actually you met them.
And I told then ED that he can sort of talk to corporate office, tie up with the Japanese firm for getting the order. But I think nothing was done and they didn't qualify, I think. That was how we lost the chance. Otherwise, BHL would have got 1 lakh tons of fabrication of bridge structures.
Great. Good evening. Samigas here.
Sir.
Sir, good evening, sir. Good evening.
Sir, good evening, sir. Sir, good evening.
Good evening, Suresh.
Sir, good evening.
How are you? After a long time.
Suresh, good evening. Dharmalingam.
Sir, good evening. எப்படி இருக்கீங்க?
நல்லா இருக்கேங்க. கோயம்புத்தூர் தானால திருச்சியா?
கோயம்புத்தூர் சார், திருச்சிக்கு வரக்கூடிய வாய்ப்பு இன்னும் வரல சார்.
இல்லையா? ஓகே.
டாக்டர் குமரேசன்
சார், நீங்க கண்டினியூ பண்றீங்களா NITT-ல?
ஆமா.
ஓகே, குட். T&I இல்ல? Department is
correct.
In fact, our 1974 batch of REC Trichy we are doing quite a lot of things to our NIT TT. For COVID also, we are raising a lot of funds, and we want to help the students through some PhD guidance, etc. But on the time varla. So I had a discussion with postgraduate students on welding career after their ME. So we want to help our youngsters of NITT who are our juniors today.
Okay.
Dr. Kumaresan,
Yes, sir.
I think we
Good
can
evening to
start.
all of you. Good evening, sir, Dr. Suresh.
Good evening.
Good evening, Chairman. Good evening.
Good evening, sir.
Shall we start, sir? Good evening, sir.
Yeah, we can start.
Yes, sir. Thank you, sir. Samida, sir, good evening. Dharmali, sir, good evening. Everybody, good evening.
Good evening, everyone.
Happy good evening to everyone. This is today we have an eminent speaker with us, our well-wisher and our friend, Dr. S. Suresh, former General Manager, WRI, and presently as a professor in Metallurgical Engineering Department and PhD College of Technology, Coimbatore. We are very much welcoming, sir. Welcome to our program. We are very happy to see your face today after a long time. Thank you for joining with us. We welcome all our members of Institute of Engineers, members of the Institute of Welding, Indian Welding Society, Institute of Metals, our committee members of all the professional bodies, and invitees for today's program. Now we welcome our present chairman, Dr. Kumaresan, to give the presidential address as well as welcome the gathering, sir. Over to Dr. Kumaresan.
Yeah. Good evening to all of you. So
Good evening.
personally, I thank each and everyone for attending this today's evening program. So on behalf of IEI Tiruchirappalli Local Center and on my own behalf, I extend a warm welcome to today's speaker, Dr. Suresh, Professor, Metallurgical Engineering Department, PhD College of Technology, Coimbatore, for accepting our invitation and also delivering the lecture on the important topic, distortion control in a large welding bridge structure. So this is a quite interesting area, and also everyone aware that DHL Tiruchirappalli is doing good work in the area of welding as well. So with a short note, I welcome each and every one of you for today's program. Thank you, one and all. Thank you.
Thank you, Dr. Kumaresan, for welcoming the gathering. Thank you very much. Now over to Dr. Engineer Samida, sir, our past chairman, to introduce the speaker to the audience. Sir. Samida, sir, please.
It is my proud privilege to introduce Dr. Suresh to all of you. Dr. Suresh had been a colleague of mine when I was in Welding Research Institute. Dr. Suresh is presently serving PhD College of Technology as a professor at Metallurgical Engineering Department. He has also established a Center of Excellence in Welding with an outlay of rupees 24 crores, Department of Heavy Industry Project, Government of India, and PhD College of PhD Technology, Coimbatore. He was a general manager at WRI and head of plant laboratories attached to Trichy. He is a doctorate in metal joining from Metallurgical Engineering Department of IIT Chennai. He has more than 43 years of experience in the field of welding research and industry consultancy. He carried out 125 consultancy projects in welding and allied fields in power, defense, aerospace, earth moving, automotive, railways, and heavy engineering, including earth moving machinery sectors. Currently serving National High Speed Railway Corporation, Government of India, as an expert committee member for fabrication of bridges for the bullet train project and development of fuselage for advanced aircraft, DMRL. Has 40 years of teaching experience in academic and professional institutions. Has won 18 national awards, including Distinguished Alumni Award of NIT Trichy. He is a certified and qualified assessor of Enable for testing laboratories. Currently serving as IWISO 3834 consultant to Roots Industries, Coimbatore, and its pumps and separation, Chennai, CCCC, Coimbatore. Customers served in the past 3 years are CBPU, Afghans, JNK, LG Coimbatore, LMW Coimbatore, L&T Coimbatore, Propel Engineering Coimbatore, Radiance and Radiance, Ashland Coimbatore, Roots Industries Coimbatore, Texmaco Coimbatore, TVS Hosur. He has been awarded with the 12 patents, has published 22 papers in international journals and presented 165 technical papers in the national seminars. He is an educator and trainer for BETZ, Asian Welding, American Welding Society, and Cornerstone Academy IW programs in India. An expert in welding and allied fields that includes welding design, fabrication, control of residual distortion and stress analysis, metallurgical failure analysis, quality assurance in welding in large structures. With this brief introduction, I request Dr. Suresh to take over.
Thank you, sir. Thank you very much for reading through the biodata. Thank you, Selvaraj, and thanks, Rajshekharan, for everything, all the arrangements. And in fact, I would like to especially thank Swamidas ji for having thought of me after so many years and giving me an opportunity to share my experience over the years, especially in this Jammu Kashmir bridge construction, which I have been associated right from 2010 onwards. Around 2008-10 was the time where it really picked up. And after my retirement in 2012, they again requested me to continue, as I know the origin from the scratch we started. So the whole bridge is coming to an end now, and the terminal date for construction completion is 2022 December. So that is the schedule now. And I would also like to thank our senior professor, Professor Ramaswamy, all my colleagues from WRI, BHEL, my students, my well-wishers, and everyone who supported me throughout this endeavor of serving the industry. Now let me directly go to the talk now. So first I'm going to present a very short video on the real bridge position today. This is the latest position of the bridge before about 15 days. So you can see the real terrain of the whole region. What is the stage or status of this construction? Subsequently, we can go into the welding details of this bridge. So let me play the video. All of you be ready. So I'm going to play the video now.
நீங்க ஷேர் பண்ணுங்க சார் வீடியோவை. சார் ஷேர் பண்ணுங்க.
Only audio is coming, no video.
இல்ல சார் ஸ்டாப் பண்ணிட்டு ஷேர் பண்ணுங்க சார் திரும்ப.
One second. I'll have to share it. Okay.
ஓபன் பண்ணிட்டு நீங்க அத இல்ல ஓபன் பண்ணி வச்சிருங்க வீடியோவாங்க டெஸ்க்டாப்ல ஓபன் பண்ணிட்டு ஷேர் போடுங்க சார். அப்ப சார் வந்துரும். அப்ப நீங்க கிளிக் பண்ணி வீடியோவை ப்ளே பண்ணலாம்.
இது போங்க ஷேர் ஸ்கிரீன்ல கீழே போடுங்க.
கீழே இருக்கு பாருங்க கிரீன் கலர்ல.
கிரீன் கலர். ஓகே அதை டிசேபிள் பண்ணி இருக்கு.
நம்ம அப்புறம் பேசுறோம். அது ஸ்ட்ரக்சர்ல இருக்கு. இப்ப ஷேர் ஆகுதா என் ஸ்கிரீன்?
இல்ல இன்னும் வரல.
Host disabled participant screen sharing.
Sorry.
உங்ககிட்ட கண்ட்ரோல வச்சுக்கிட்டீங்க.
இல்ல மறந்து போயிட்டேன். Now you try, sir.
Can I start?
Start.
Share ஆகல.
ஸ்கேன் ஆகலையா?
ஷேர் ஆகல. ராசே ஷேர் ஆச்சா?
இல்ல ஆகல.
வரல.
சார் நீங்க சுரேஷ் சார் வீடியோ வந்து டெஸ்க்டாப்ல ஓபன் பண்ணி வச்சீங்க சார். ரன்
இப்ப வருது, இப்ப வருது பாருங்க.
வருது.
Okay sir, now we play sir.
So that is the latest position. Are you able to see my slide?
Not yet.
No, you are not able to see. Look, the video clip ending is there. Now it's visible, sir. Now your slides are visible, sir.
Yeah, so you saw the video. That gives you the latest position of the bridge where you saw the arch. The whole bridge contains three major group of structures.
The voice is not audible.
Now your voice is not audible. You have to come to close to mic, or some adjustment you have to make.
Okay. Am I audible now?
Now okay.
Okay. Can I?
Okay, sir. Now okay.
Right. So what you saw is the arch of the bridge, as you saw. The arch is the main structure which is going to take the load. And you see the pier, which are the vertical sections. These vertical sections end up with the same plane where the deck structure is going to be installed and commissioned. So the top flat is a deck structure. The vertical supporting structure between the deck and the arch is called the pier, and the arch structure. These are the three basic assembly structures of this bridge. As you can see, you would have already seen in the video, there is no support per bed. So it is supported on either sides of the mountain with a huge foundation, which is more than 30, 50 feet or so. It's a rock and complete terrain environment. Hello? I think everybody has to switch off their mic so that you can hear me. Shashankaran, you have to request everybody to switch off their mic.
Ashar, you can mute this not from your side.
Mr. Surendra Singh, switch off your mic.
Please, all of you, switch off your mic so that you can hear me. Is it okay?
Yeah, now okay.
Am I
Now it's
audible?
okay, sir. Now it's okay.
Yeah. So you can see there are two rope bridges. This is the pillar for the rope bridge. You will see subsequently a rope bridge as I show you. Through this rope bridge only, the total erection takes place. And there are two sides of this bridge. One is called Kauri, another is called Baktal. This bridge comes almost at the center between the Jammu city and the Baramulla city of Kashmir. So roughly about 150 kilometers from Jammu city, and from here another 150 you reach the border of India. So to reach this place, you have to go from Jammu via Katra. I think you would have heard about this Vaishnavi Devi temple. Many of you or some of you might have heard. You have to cross that place called Katra. After that, there is no real road. You have to go through a hilly region, a lot of hairpin bends, about 20, 25 of the hairpin bends you have to cross, and then reach this height. This height is almost as tall as our Ooty. So it's a very hilly terrain, pretty cold, pretty hot, and so on. And it is next to impossible to take the fabricated pieces to this site. So we had to erect. When I say we, I'm fully supporting the contractor who is Afcons Infrastructure Mumbai. So this Afcons Infrastructure Mumbai is the main contractor who has taken up not only this bridge construction. On either side of the bridge, there are two tunnels. On the left side, Kauri side, as you see this bridge, there is a. So on the right side of the bridge, you have a 5-kilometer tunnel. 5 kilometers, please note that. It is coming through two mountains, and the railway line is coming from Katra, Riyasi to this place. Now, after crossing this river, it will go through another tunnel of 2.5 kilometers. It's a very exciting kind of a project, which is going to be the icon of Indian construction of such a bridge. So this is the thing. As you see here, on one side you have a hilly terrain, a real, not a ground, but up and down mountainous terrain. So there are a lot of concrete piers coming here. Similarly here, and this side, you have the Kauri side, which is having 5 kilometers tunnel. And this side, on the left, you have another tunnel on the Baktal side. And this is the river, and you have the arch, you have the pier, and the deck structure. So this is the overall elevation of the Chenab River Bridge. And now you can see, you saw this in the video. At the moment, the arch is already fabricated and erected. All the three structures are welded and using high strength friction bolts. We join two typical structures. So it is a welded, bolted structure of the bridge. And you can see the top view of the deck structure. So this is the ground level from the Kauri side. These are the engineers' quarters. And here we have a guest house where we used to stay. It's a helipad for people, big shots to come and see. So this comes from the tunnel and it goes to the river. And here there is a bridge crossing. So the Chenab River comes like this and takes a turn and goes towards Jammu and Pakistan and further down. So that is the overall view. Now you can see the close-up view of the deck structure on the top. So these are the engineers' quarters and so on and so on. So this is the close-up view of the arch structure, just erection completed. Now they have to fill up with the concrete the entire top and bottom box section, which is the section view of the arch structure. So they will be filling up with full concrete so that it can go around. This bridge is designed such that it can withstand 7, 8 Richter scale. That means earthquakes cannot so easily dismantle this bridge, and it is also anti-sabotage design. So a lot of care has been taken for design of this bridge by Denmark and Netherlands. About a big bridge design company has designed it, and the railways is going to be, the Northern Railway is going to be the customer, and Konkan Railway has played a very big role in the initial stages of this construction, location, etc. So the contractor is the Afghans. So coming to our welding. So what you saw was the arch. This is the pier and this is the deck segment. Now this deck is, the top deck is made up of 68 segments, each 60 tons. The piers have different lengths, the longer one, little shorter, very short, etc. They are all box sections. I'll be showing you shortly. The arch beam supports the deck pier and the deck plate and transfers the load to the foundation, which is on the either side of the bridge. So this is the model as we made it there. You can see for people, general public to appreciate it. So this is the arch structure, the pier and the deck structure and the top. So now a little more about the construction features of this bridge. This deck segment is also called a viaduct assembly. So people can simply walk through the viaduct and cross the bridge for maintenance and other purposes. And this deck segment to deck segment has to be assembled. So, and then this deck segment assembly has to be launched from both sides. As you know, as you saw the terrain, you have no supports from the river side. So the supports are given only on the both sides of the mountain. The lifting is done by the rope crane. As you saw, there are two pillars, red color pillars. There is a rope crane which can handle 30 tons at a time. So two cranes, 60 tons is the kind of handling facility we have. And it's a very risky job. As you know, it is a 360 meters is the elevation from the river. And then we have a pier fabrication, arch fabrication. I'm sorry, there is a spelling mistake. I'll correct it. Construction of rope crane and end supports, launching of the arch, pier and deck structure, launching of the deck segment and bolting of the assemblies. These are the major fabrication tasks that you have. Coming to the challenges, this is the welded and bolted type of a structure. And the first challenge is you cannot transport prefabricated structure to this site. As I told you, the very, very narrow roads and lot of hairpin bends, you have to fabricate it near the bridge erection location. and fabrication yards had to be constructed at the site, and all the resources have to be moved from the ground level to the site, which is about 4 hours journey from Jammu site, and handling facilities are inadequate, and environmental conditions are very harsh, pretty cold in the night, hot in summer, and proper roads are not available, and launching of structures and erection, the toughest challenge, and it is planned from both sides of the bridge side. And practically around 25,000 tons of fabrication was involved with the welding and bolting. And we had fabricated 3 major assemblies: arch, pier, and deck structure. The materials used are E250 C grade carbon manganese steel and 410C HSLA steel, that is high strength low alloy steel, with a fine grain size of 7 and 8. So we had to choose this steel because in arch structure, because we required a very good toughness at -40. That was the design criterion. And thicknesses involved are 12 to 115 mm in various structures. And the construction code was BS 5400. It's a European design. So all ISO standards apply here. So it is a fatigue loaded structure. So it is fatigue design, and construction was made as per part 11 of BS 5400. So all features of the weld joints were done as per 11 part of 5400. And it is very most critical requirement was the distortion control, because the arch has, the bridge has got 2 curvatures. You would have seen in the top view, I'll go back to this slide. I can see, if you see this picture, you can see the, can you see the curve? Can you see the curve of this deck structure in the ground? So this is one curvature, and another curvature is, I don't know whether you can visualize this. You can see this arch. They are wider here and getting closer in the middle, and again becomes wider. Can you see that? So that means it is tilted inwards as well as there is a curvature outside. So both the arms of this arch structure are having an inward tilt, plus there is a curvature along the length. So it is a double curvature design to give a aesthetic view. So this arch structure has got a double curvature. The both the deck structure and the arch structure has got a double curvature, and the fitment tolerances, because you have to bolt each of these structures plus minus 1 mm, 0.5 to 1 mm is the clearances given in the bolting between one structure and another. So this became a very big challenge, how we are going to control the distortion of this structure. So this double structure had to be controlled in a very strict manner. And we adopted both before welding, during welding methods to control this distortion. And we also did a lot of innovative things. As we go along, I'll tell you. And this erection had to be proved with a trial erection in the ground level, marking, then shifting it to the side. And the welding procedure and the PQRs were done as per ISO 15614 standard, and the welding defects were evaluated as per ISO 5817. So a completely European standards, ISO standards were used. And I was serving I'm still serving this Afghan structure as a IWE, that is International Welding Engineer Support. I am providing them. And the welding processes used were gas metal arc welding, Cascode arc welding, submerged arc, stud welding, and SMAW to the minimum extent. The maximum percentage of welding for these 25,000 tons was maximum SAW, next FCAW, stud welding, and minimum level of say 10% to 15% was only shielded metal arc welding. And you can see the Kauri site now. So this is the fabrication site where we fabricated the deck structure. Actually, we started fabricating the deck structure. Subsequently, another workshop was built in Surundi, another place which is 4 kilometers, where we started the fabrication of pier structure. Subsequently, we built another yard as we went along, where we started fabricating the arch structure. So 3 workshops separately installed for fabrication of 3 individual structures were made. And what you see is a typical deck structure fabrication shop, where you can see the deck structure model. Now, what we did was, before we did the real fabrication, as per AWS B2.1, we did the mock-up structure. The length was real. The width was real. The length was only 3 meters, though the actual length is 8 meters. So with besides the standard test weldments, which are used for our establishment of WPS and PQR, we also proceeded with a mock-up fabrication. Mock-up in the sense, the cross-section is same, the width is same, only the length is minimized. So this was done, proven that all our procedures and our PQRs were established in the real structure. Then only we moved to the actual fabrication of the structure. So all our sequence study, assembly, welding sequence were, initially tried out on this mock-up structure, tested completely by NDT. Then we proceeded to the actual job. So this is the model what you can see. So you can see now the structural complication. So here, this is the deck plate, about 13.5 meters width, 8 meters length. This is the length and this is the width. So this can carry 2 rails, 2 trains at a time. One can forward and backward. So 2 railway lines will be launched in this bridge. And you can see there are about 6 secondary girders, 2 main girders, which are deep webbed girders. You can see the deep webbed girders here. And here also you are seeing the actual cross section. So these 6 are the secondary girders in blue. The green is the deep webbed girder, which is the main girder, and all other stiffeners, about 16 of them. Totally about 25 longitudinal sections are there, and 2 cross sections, yellow in color. These are the transverse sections of the segment. So the total segment, and in the bottom you have box sections called lattice structure. So this is one single segment, which is about 68 tons, and this segment contains about 25 longitudinal joints on the deck plate, about 8 to 10 joints of butt joints in the deck plate, and box sections, lattice structure. Totally about 35 to 40 welded joints in this structure is what you see. And now you can see the tech law, that is the solid model drawing of the whole structure. This again clarifies you what is the type of structure. So this is the deep webbed beam, this is the cross beam, and these are secondary beams, which are 6 in number. These are horizontal stiffeners, these are the cover plates, and the cross brackets between the main web and the edge of the segment. So this is the overall structure. So what we do, we first make the structure, make another one, put it down on the erection bed, join them as an assembly, push it forward. So the third one is first 2 are pushed out, third is pushed down from the ground level, I mean the shop level, then joined with the 2 pushed out. Again, the fourth one is made, put down, joined with the first 1, 2, 3 and pushed down, pushed along the length. So like this, we keep launching, fabricate, assemble, launch, fabricate, assemble, and launch. So this is the sequence of our fabrication. So if you come to the main welding part, you have a deck plate subassembly which has 6 plates, and the following sections are welded with as a subassembly 1, where I'll show you now. For example, this is the base plate. The orange color is the base plate, where you can also see a small tilt in the diagram. This is not distortion in the figure. This is the pre-setting of the bridge, so that when rain comes, the water will automatically drain through the central hole. So you can also see there is a small curvature here. So these are the 1, 2, 3, 4, 5, 6, 7, 8. These plates are joined together in this case. Then horizontal stiffeners, longitudinal stiffeners are placed. Then cross beam structures are placed. Then vertical deep webbed girders are placed. So now you get the assembly. It is welded in a sequential manner, and then it is brought to this launch pad, and then it is lowered where it is assembled. So deck plate fit up and welding, horizontal stiffener, cross beam, secondary girders, main girder, horizontal stiffeners fit up. Like this, we go in a specific sequence. So first deck plate is welded, then horizontal stiffeners, then cross beams, secondary beams, then cross beam to secondary beam in a sequential manner. In phase 2, we weld the horizontal stiffeners, cross brackets in a particular sequence. We measure the distortion. Again, if there is a deviation, we change the sequence. In the second phase, we complete the welding so that the longitudinal diagonals, the squareness, the height, the width, and all the dimensions are as per the drawing. So this is what we have done. So I'm getting into the much more details now. So this is your deck plate assembly fixture, where we keep the deck plates and weld them. So you can see the curvature more closely. So here we have decided both the direction, the welding sequence and the weld sequence, such that the distortion is kept to the minimum. And we used SysWeld software in our center to estimate the shrinkages. We could not use it for predicting the sequence, as this structure, if you want to run an FEM analysis, we estimated it as it may take about 15 to 20 days. So that much time was not available. So we used this software for predicting the shrinkage, and then with my analytical method, we predicted the sequence and ran the sequence in the mockup. Once we got very good results, we applied it straight away into the actual structure. So you can see the diagonals were being monitored after every stage of welding. And sometimes we use ceramic backing so that you need not turn the plate, because turning the assembly is a big job in the site, especially because we have handicapped with the lifting capacity. So here, if you see, we determine the welding sequence, welding direction, the welding order, everything was decided initially, and then we applied it on the mock-up. When everything is tested, we applied it on the actual structures. We applied sometimes 2 welders, 4 welders, according to the availability. So now then, after the basic plate is welded, I insert the secondary beam and the horizontal stiffeners, 6 of them, secondary beams. Now again, we applied the sequential welding at this stage. We had to do this step-by-step welding, because once you insert the main I-beam, the welder cannot go inside and get an access properly. I mean, the welder will not be able to get the lead angle and the work angle for obtaining a good welding quality. So we had to consider that also in our welding sequence, the direction, etc. So all these were predetermined and we applied the welding. And now you can see the main girder is already tacked or assembled. The secondary girders are in place. You can see the the longitudinal stiffeners goes through the cutting or the opening of this cross girders. So this is the main girder assembly, which is a big challenge for all of us. And all these secondary girders and cross girders were completely done in semi-dark welding with a fixture which was designed at site and applied at site. So we had to do a lot of fixturing design, assembly, and then using it for actual fabrication. Now this secondary girder to the flange are all full penetration double bevel fillet T-joints. So after welding one side, you had to back gouge, regrind and weld it again with semi-dark welding. Sometimes when the thicknesses went more than 32, 43, etc., we did the root weld with the GMAW, then the back gouging, again did the other side, then continued with SAW process with medium manganese wire and sometimes high manganese wire for getting the strength of the 450C material, 410C material. Now this is the main girder assembly. As you see, this is about 2.5 to 3 meters height. And you have a horizontal stiffener plus vertical stiffener. The flange thickness is of the order of 63, 55, 45, and so on, depending upon whether it is starting of the bridge, middle of the bridge, or end of the bridge. So along the length of the bridge, the thickness of the flanges, web and flanges vary. So you have to have procedures accordingly. Again, we applied a weld sequence such that the squareness of this plate, it does not have a bend camber, so that welding with the deck plate will create a problem for us. So these are the welding sequence followed. And you can see the various snapshots of how we welded this main girder using the makeshift fabricated fixtures at site, and again automated or mechanized semi-dark welding was done here, and then tilting it again, doing the welding after the back gouging, back grinding is done. So this is the tractor which we use for semi-dark welding. You know this, all this. So after that, we had to do the stiffener welding with GMAW, sometimes FCAW. If it is fillet weld, we use FCAW. If it is a groove weld, we use GMAW, because we felt that in a groove, there are chances for lack of fusion penetration if the quality of the wire were not good enough. So we took a lot of precautions in establishing the process so that at any point of time, we should have a higher quality of construction. So that was being done here. And you can even see the recess folds. If you see the recess folds, or you can see the recess folds in this. Sorry, 1 minute. Now you can see the recess folds where we have relieved the fillet weld from the transverse weld and the web to web joint. So that is what you are seeing. So now coming to, now initially we keep the bridge, 1 second. So initially we keep the bridge in the upside position where you are welding all this. Then we are doing the assembly welding. Sometimes we also use the what you call low cost automation techniques for welding the fillet weld after completing the groove weld. So this is how we went about welding the cross bracket inner parts of the construction. So now we are coming to the assembly, fit up of one segment with another. So one segment of 68 tons is now assembled with another 68-ton segment. And you are also seeing we locked the entire structure using the lattice structure, which is again a box section structure, as you see from inside the bridge. This is already tilted upside down in this case. Now for tilting, we again fabricated a huge A-type crane, both cranes, now lifting and tilting upside down. Because remember, the deck plate are only one side welded by Samaida. After tilting, we back gauge completely and re-weld with semi-dark welding to see that full penetration welds are made. Now all these butt joints and critical full penetration joints were also tested by phased array ultrasonic testing technique. Both conventional UT as well as phased array techniques were used. At this point, I would like to thank our Dhanashekaran, who also helped us in establishing the procedures, giving his comments on how to go about evaluating this phased array UT technique, because till today, till that time when we tested it, procedures were not available on the acceptance criteria of this phased array UT technique. So there are a lot of challenges were faced in NDT also. And we also established a laboratory at site, which is NABL accredited laboratory, because sending the specimens back and forth took a lot of time. So this is for shifting, rotating the segment, as well as lowering the deck segment. So now this is the position of the deck segment after rotation. So this will be lowered downwards. So this is the edge of the shop. Here below, there is about 25 feet or below. The deck segment is lower. It is assembled with the already prefabric, the first segment welded and then pushed to the side. Now you can see a clear picture of the cross section as you see. And what we did was, in order to assemble this one segment with another, we had cut out about 300, 400 mm on either side, fit up properly, then weld that also. So this assembly welding was very challenging, as you see here. This is one deck and another deck segment. So this white line or the assembly welding. So here, here, here. So you have about 16 main joints, nearly 25 joints all along the cross section, main web to web joint, flange to flange joint, here again web to web and flap to web. Totally along the cross section, you have quite a lot of vertical butt welding, horizontal welding, again overhead welding, and so on. So here you can see the cross section. So 1 to 16 are longitudinal stiffeners, 70 to 22 are cross girders, 23 and 24 are main girders. So we numbered everything clearly. We made a perfect sequence in which this has to be done. And after every set of welding, like when you weld longitudinal stiffeners, I stop and measure. Again, after welding the secondary girders, after welding, I stop and measure. So it was a step-by-step procedure, because it is next to impossible to predict the distortion of such a large complex structure. So you can see the bottom side view and how we went about welding in a very specific sequential manner. And totally there were 35 main joints in the deck-to-deck assembly, and sequence was split into 2 stages. All are multi-pass welding. So we split that into 2 stages, stage 1 and stage 2, where we do all the welding in a sequential way in stage 1, stop the welding, get it quality check, dimensional quality, if whether the diagonals are okay, the length is okay, the width is okay. Again, restart the filler pass welding in a special sequence so that we get to the final dimensions. And if the deviations were not significant, we continue with stage 2. So like this, we had to do this sequential welding. We went from center towards edges. As you see, we weld alternatively the web and flanges. So after completion of welding, we come to the top where we do the SAW welding after back gouging of the root and the first side weld. We do the final welding with the semi-dark welding and test it by mechanized phased array UT, where the data was completely logged in the computer and it was evaluated by various inspection people as well as UT experts to clear this weld. So this is the challenging job here. So I'm sorry, the little bit deviation of this plate. One of the most challenging piece was here what you see, the main flange joint. There is already one vertical joint, two fillet welds here, and the main butt joint. Incidentally, if it are for controlling the distortion, anybody would have preferred a double V here. But here, if you see, it is a single V. Mainly because the railways did not allow us to do overhead welding. And somehow they felt that overhead welding cannot produce a good quality weld. So what we had to do was, we went for a ceramic backing joint from the top side, the root welding. After welding this, we went about welding in a multi-pass joint. As you know, any single V butt weld will produce heavy distortion. And in fact, when we first welded this in the mock-up, we faced a problem of buckling of the web plate. So immediately we told the designers, and this buckling was avoided by putting extra stiffeners, which was stress caused by welding. That means compressive stresses were introduced due to the angular distortion on this web plate. So we had to change the web plate design by introducing two more stiffeners on either sides of the butt joint. This was suggested by me, accepted by the designers as well. So what happened was, because there is going to be a heavy stress in this plate, especially 63 mm, 75 mm flange to flange plate. Even though you do preheating, post-heating, whatever you want, the stresses could not be brought down as low as we would like to have. So what we did was, we also did local post-weld heat treatment of this joint only, where three weld joints are meeting. One is in the y-axis, one is in the x-axis, and your weld is in the z-axis. So sigma x, sigma y, and sigma z. All these three directions stresses are meeting at this point, creating a triaxial stress state. So I felt that you are running into a brittle fracture condition in this case, and a lot of people resisted me. I produced a lot of evidences of how a brittle fracture can occur here, and especially the weld joints with notches can create a brittle fracture. So finally, they agreed with a lot of resistance. So we did the stress relieving of all these joints, especially this joint, what you see here, especially above 50, we had to go for, because the joint is under heavy restraint condition, the residual stress is likely to be active in all the three directions. And if you take a small weldment from this weld, it will be subjected to triaxial stress state. So this is what we did here. So all the welding directions are also seen here. So once we complete, so now you can see from this shop, three segments have already come out. This is the launching nose, as we call it. So when we push from here, this launching nose goes and sits here. So it drags this segment and then moves along. So as you see here from the other side, so you can see the deck structure is pushed from one side and the nose, launching nose is coming out. So you can see from the shop, it has come out so far. In the ground level, you are seeing a lot of concrete piers, which is holding the deck plate. And this is the rope crane mast, which is going to handle this above the river. So that is with respect to deck section. Now coming to pier, we had established a separate shop for pier fabrication. So this is the pier 20, a typical pier 20. All the four are box sections. The height varies and the vertical members are box sections, as you see, and they are not simply box sections. They are boxed with a central web plate as well. So the central web plate protrudes in all those nodal points to which your cross members will be connected. So it's a very unique design. So you can see the snapshot of this SolidWorks model, where you can see the top bearing plate assembly, and you can see these are coming out of the web plate of the central pier section. I think you will understand soon what I mean. So these are already pre-drilled and welded. So they have to match perfectly with the matching section of the assembly. And remember, our tolerance is plus minus 1.5 along the length of the beam. And each length of the pier section will be 11 meters, 12 meters, and so on. So we are expecting a very close tolerance after welding. Now you can see what is coming out. So through this web plate, this comes out. So you can see the box section. This is the top flange, bottom flange, and the side web plate. And can you see this? Through this web plate, another link plate is coming to which the connections will be made. So a very interesting typical cross section. So we used mechanized semi-arc welding for welding all these corner joints with a bevel fillet corner joints. So these are the joint designs here what we use, whereas here inside welding is done by GMAW or flux core welding as the case was. So you can see first we make the I section. You can see in the ends it is thicker, in the middle it is thinner. So all these thickness variations are also there. You can also see very clearly in the end it is thicker, in the middle it is thinner. Flanges and webs as well. So all these joints were made by semi-arc welding, and you can see now the construction. First I make the I section by semi-arc. So this web plate is welded with the two flange plate. Then I insert one web plate here, closure plate, another closure plate. It becomes a box with a central web plate as well. So this is a typical cross section. And here the drilling was made in situ for connecting it with the other sections. So you can see the web is protruding out where the connection, the bolt holes are already made, both on the flange, top flange, bottom flange, and on the web plate. And edge preparation is already done on this plate so that it can be connected to the other plates. So you can see the plate in condition, preheating of the corner joint and welding taking place along the edge of this corner box sections, corner joint with a bevel plus fillet. So this was the construction feature, and you can see the weld being completed. The view gives you also the distortion control of the entire beam above box section. It's about, if I am right, about 14, 16 meters or so. So this is the completed pier section through which your gusset plate is coming out, which is already welded inside with the web plate as well as the outer web as well as inner web. So this is the close-up view of the semi-arc welding of the box section. This is the fully completed pier fabricated beam, where this is the outer flange, inner flange, the middle flange to which this gusset plate is coming out. The ends are all gusset welded. I mean bolted. For bolting, you have already the drilling in place. Then we come to trial assembly where we take it out and we completely make a trial assembly of one full section. That means from one node to the next alternative node. So 3 nodes are assembled together, numbered, checked for its alignment, and you can see the alignment now. So the holes are all in straight line. And when you put this was done by 70-30, that means, we put a double pin and then align properly and then check the alignment with the go, no go gauge. So that was done here for trial assembly by an inspector. Incidentally, welding was Afghans and one agency for welding, 7 agencies for inspection. Very interesting. RDSO, ISO, railways, Afghans, KRCL, like this, so many agencies are checking the alignments, both for alignment of the edges as well as matching of the holes. So now coming to the arch structure, which you saw, the arch structure is the bracing between the two, top arch, bottom arch, left side, right side. So there are 4 arch box sections. These two are connected. Top as well as bottom are connected through these green arch bracing, as you see here. So the box sections of the arch have double curvature, as I told you, 2 directions along the length. The end of the sections are pre-drilled and are connected. The arch beam comprises of 2 parts, left and right, left side, right side, left side top, left side bottom. Here again, from the arch, the gusset plates are coming out, to which the other gusset plate of the pier will be connected. So this is the typical construction. Now you can see the cross section of the arch plate. So there are 2 box sections connected with the flange. These flanges got T sections right through. So typical 2 box section at the edges with a flange plate connected by completely longitudinally running T sections right through the arch section. So one typical section again, one arch section will be of the order of 12 to 16 meters according to the location where it is used. And these are box section bracings. Green is the bracings of this cross section. These are nodal points where in the deck also we have a gusset plate to which these things will be welded. Similarly, in the bottom, this is the top arch and the bottom arch, you have a protrusion of the gusset plate to which these will be welded. So this is the cross section where there is the left side box, right side box, and 3 major T stiffeners welded. Inside, you have stud welds, and all these stud welds are made by arc stud welding process in the side. And after completing, through this manhole, we will be filling up with concrete completely. So it becomes a very rigid section with outer wall as the steel box and inner completely filled with concrete. So it's a huge, heavy structure. Once it is erected, nothing can shake this structure, and it can go with the highest wind speed of an hurricane. This can withstand. So that is the kind of a design made. This is the gusset plate, as I told you, which protrudes from the arch section, to which the pier gusset plates will be welded. Again, they are pre-drilled, and butt joint is welded with back gouging, and suitable clamps are used. Now you can see the already drilled plate. There are a lot of butt joint of this gusset plate is butt joint. So here another butt joint. All are UT, both conventional and phased array ultrasonic testing done. These are the stud welds which were done and tested before fabrication, before attempting to do the actual welding. So these are CNC drilling machines for drilling these holes with very high accuracy. So they are all stacked together, matched and welded. And after welding, again, we check the alignment, PCD, etc. with go and no-go gauges. You can see the inside section of the right side, left side web. This is the top flange and the bottom flange. In the ends, they are already drilled for splice plate welding, splice plate connection between one arch structure and another arch structure. So all welds are also shown here. You can see 6 mm, 12 mm, double fillet, all round fillets, etc. So now you are seeing the fabrication where the stud welds have already been made and the pre-drilled is already available. And what we do, first to do this, then put the diaphragm plates with holes for pushing the concrete inside. So after that, we put the left side plate, right side plate, complete do welding, put the fourth plate and then close the box with proper welding and testing. This is the diaphragm plate for this box section. So you are seeing 12 mm fillets done on either side. And here we do single fillet from inside, and outside we do bevel plus fillet, because inside you can't go in after putting the fourth plate. So that's how the design and fabrication was done. Now you can see the left side plate, the right side plate is done, and the flange plate is done. We do all the stud welds are seen here. So we have welded this plate, diaphragm plates with fillet welds. Now we do all the checks inside. Then we put the fourth plate. Once it will cover, it is difficult for the welder to go. So only certain welders can go inside and weld it. So this is how the fabrication of the arch structure was done. So here you can see in the cross section. First we do this bottom plate to top plate, then diaphragm plates, then put the fourth plate and complete the assembly. So this is the completed assembly of a T3 plate. T3 is top plate, side plate, web plate, right side plate, etc. This is the gusset plate where the welding is done. So after doing this section, we come to the flange section. So here one left side and right side is done already. Now we are putting this plate in which T stiffeners are welded to make the assembly. So these T stiffeners are again, you can see this is the box section, right, left, and the flange plates are welded to this both sides of the box. Now this is again welded using GMAW, FCAW sometimes, and this whole section is now ready. You have also a cross beam, a cross stiffener, which holds this box completely. So this assembly is now shipped to the site. You have top one, bottom one. We put also the bracing, and as a whole, we take it to the site, and individual assembly, we take care that it does not exceed 30 tons per piece, so that erection is completely possible. So what you see is a typical assembly which is completed. This is the whole assembly with cross beam, longitudinal section, and the plate. Now you can see the actual section, left side box, right side box, flange plate with T stiffeners and cross stiffeners. So this is the arch box section with the flange and stiffener. This is the arch beam assembly as we call them. So this is further connected with the bracing and then taken to the site and welded. These are the bracing as you see here. Again, box section with gusset plates. You can see the gusset plates connection to which these bracings will be connected. The top arch assembly, the bottom arch assembly are connected through this gusset plate, this green. is called the bracing. This is connected both top and bottom as well as left and right side and left side top, right side right top and left bottom. So there are both this way and cross way. The bracings are connecting the four together as a full arch assembly. So these are the foundations as you see here, over which the arch will be erected, one on the left, one on the right. And from the foundation, you have a gusset plate coming out to which these box sections will be assembled. You are seeing the foundation and erection of the base frame, which is a huge box of the height of 6 feet or so, though it looks small in your photograph. So this is how the frame was done. So from here, we start moving. So it is held in a rope crane and as well as the pier section. So after this, we connect another one, bolt it, take the rope crane. So you can see the rope crane mast as you see. I don't know whether this picture is clear. You can see a dark line here. This is the rope crane, crane and also another crane which is holding the arch section until you put the another arch, bolt it until that it will be holding. Then the load is transferred to the left side. As per as right side, there are a lot of mechanisms for that. So slowly, the arch is coming from either side. And finally today, what you saw in the video, it is arch structure erection is completed. The pier sections are in progress. The launching of the deck segments have come to the place where the river bed is there. And the project will be completed by 2022. So that is an overview of the welding details, the construction details, where we are today in this prestigious project of Government of India. So we from WRI, we started this project way back in 2006-7 or so. At that time, we had our Uma Shankar, who was also coordinating this project. Subsequently, the project took a little time. Suddenly, the railways changed the specification from a single line to double line. So when it became double line, the design had to be completely redone and the entire procedures had to be redone. All the undone. For the past 1 year, we have been affected by the COVID restrictions. So again, the site has started the construction, and I wish the Afghans team a very big success. And now only the erection work is going on. All the welding work had been completed by 2019 end or 20. So only the erection work is in progress now. So that is the overview of what I felt. All of you should know the details. I thank you once again. I thank Samidas and all the Rajshekharan and all the coordinators of Indian Welding Society. The first is Institution of Engineers, Indian Welding Society, Indian Institute of Metals, our Professor Ramswamy, who is our senior professor at our PhD, all my colleagues at PhD, our colleagues at WRI, who played a very big role in shaping me to this level. Our thanks to Dr. Dharmalingam, who also contributed in adding ideas our construction. So, I mean, there is a very big list of people whom we would like to thank. And please forgive me if I, missed anyone of you. So this project is nearing completion by 2022. And this is what I would like to share. I once again thank all my students, faculty members of both NIT, PSG, and so on, all those who contributed to this construction of this bridge. Thank you one and all. If you have any questions, you can come forward.
Congratulations, Suresh, for a good
Yes, sir. Carry on.
I'm Sridhar. I'm Sridhar, your classmate.
Oh, okay. Right.
Good job.
Thank you.
Dr. Suresh sir, I have a query, sir. It was excellent, president, outstanding. We enjoy. You took us to Kashmir tour. Nearly it was
Hey, you have
interesting.
to be little slow. You have to be little slow. Boss. Please remember you are online. You got to be little slow. Okay.
Oh, okay, okay, sir. Thank you, sir. It was an excellent and outstanding presentation. You took us to Kashmir tour. Thank you for that. And I have a query, sir. What is the project cost, sir? Can you?
This bridge.
Hello?
See, the project cost means road laying, site fabrication, site construction of the maybe about 5,000 crores or so, around that.
What is the cycle time? Is it 10 years, sir? When it was started?
See, the problem was it started well. Lot of hiccups were there on the way. Suddenly, until 2014, the bridge construction was going in a very slow pace. Especially after 2018 or so, the real speed has picked up now. And originally, it was supposed to be completed in 2019-20. Now, because of this COVID restrictions and so on, it is schedule is 22 December.
Right, sir. Thank you, sir. Thank you, sir.
Sir, Dr. Suresh, sir.
Yeah.
I am Ravi Rajan speaking.
Oh, how are you, Ravi?
Fine, sir. Fine, sir. See, I am a great fan of your orator skill. I am a great fan, and you have such a complicated structure. You have explained it like a story, and we have traveled along with you during all the fabrication activities.
Ravi Rajan, sir, your camera is off.
My camera is off.
Yeah?
1 minute.
No.
No, my camera is on.
And now you are okay.
Okay, 1 minute. I am not able to see all of you.
So you can do one thing, sir. You can stop sharing so that then you can go to gallery mode. You stop sharing, then it will be easy. Yes.
Yeah, okay. Now I got
Yes,
it.
yes, sir. So I have, it was a great pleasure in listening your presentation.
Thank you.
And I really enjoyed it. From the moment I started it, every moment, it was enjoyable. And it was like listening a story. You narrated it in such a way. It's all beautifully done, sir. Thank you.
Thank you, Suresh, for very nicely outlining some of the complicated problems you faced in solving the most important problem. Is going to be a very good, prestigious project for India.
Thank you, sir, for joining us and sparing your time. Thank you very much.
Hello, Suresh, sir. I have some question.
Yeah.
Good evening, sir. My name is Batmanaban. Where are the plates are procured, sir, for this fabrication, all the structural plates?
It's again another story. See, there are so many stories here, which I couldn't cover. Actually, originally, we ordered the plates with Rourkela and I think one more, if I'm right, Rourkela and one more plant. Originally, we wanted to have a normalized and tempered steel plate. I mean, each 250C and so on, because the specification called for isometric, what you call that, the properties in all directions to be same. So we wanted to have a normalized tempered steel plate, but the steel plates were ready to offer only controlled rolled steel. So there was a very big argument between RDSO, the railways, organization, and the steel mills. They were telling it is equal to, I think Professor Ramsamy is smiling. He knows the inside out. Whether they are same or not. There was a very big debate which went on for 6 months or so. So the designer was telling, we need as per ISO standard. Whereas these people are telling controlled rolling is same as normalized and tempering. And then we referred to BHEL. BHEL was telling that when the plates were above 2 inches, it has to be normalized and tempered. For smaller thicknesses, it is okay. So finally, we, after 6-7 months of what do you call this, negotiation or something, we zeroed in on Urkela and Viloy plant, if I'm right, to get these plates in place. So a quality engineer was placed at the steel mill, who also measured the properties in longitudinal and transverse directions, as well as the grain size was measured. And in some locations, we use a Z grade plate, that is through thickness ductility, what we call as a European standard straw value, STRA. Short transverse reduction in area, we fixed it as 25%. So this was also checked for higher plate thicknesses from the mill. So this is the story about the plate specification. Right.
Yes, sir. Yeah, thank you for your explanation. Any CTOD tests are done, sir, for higher thickness plate, for example, 100
No,
mm thickness?
CTOD we didn't do. We did only straw quality plates, which were accepted after UT testing, plus straw value. And the CTOD was not done in this case. Actually, I argued that if you want to eliminate stress leaving, we can do CTOD. But we chose a softer option of doing the site heat treatment for only those joints which were exceeding 55, 63, 75, and so.
Okay, sir. Thank you. Thank you for the explanation, sir. Very nice presentation.
Thank you. So thank you, Ravi. Thank you, Uma. Thank you, everybody, for sparing your time listening.
Thank you, Suresh. Thank you. Bye.
Thank you.
It was nice to listen to you.
Yeah, thank you. Thank you all. Thank you, sir.
Thanks, Suresh. Thank you very much.
Suresh sir, wait, some more vote of thanks. Please wait, please.
How are
How are
you?
you?
Hi.
Thank you.
Nice,
Thank you so
nice
much.
to hear your explanation. Fantastic
Sridhar.
explanation.
Yeah.
Damn good. Yeah. Hello, Ma.
Very, very nice.
Yeah.
It was a very good presentation, sir. We enjoyed with you, Suresh sir. We remember the moments what we had a friendship long years for the 4 decades. I remember the first single wind box where you accompanied us and you made it really. I remember the first wind box we fabricated shop, 4 wind boxes, and we was it was very much appreciated our top management. Thank you. You were with me at about 6 months. I remember. Really we enjoyed. I remember all those moments. Now over to Dr. Kumaresan for announcing the next week's program, sir. Dr. Kumaresan.
Yeah, thank you, Dr. Suresh, for your wonderful presentation on the topic. So now presently I'm the Dean Students Welfare NIT Tiruchirappalli. So I'm extremely happy that our alumnus is presenting to Institution of Engineers Tiruchirappalli Local Center. And now, prior to announcing that, next week program, now Institution of Engineers, now they are conducting election for committee members, council members, as well as Tiruchirappalli committee members. We have circulated to all the corporate members, and all the details will be available in the website for, voting to the candidates. So it will be in online mode. So therefore, all the corporate members, I request that please look into go to the IE India website. Link I have already typed in the chat box. So you create your username and as well as password, keep it ready for voting purpose. And shortly we will circulate the screenshot of the procedure, how to enable this login in IEI India also. I'll circulate it through our email ID. So now next week lecture, we have organized topic is industrial automation using embedded systems. So speaker is Dr. Sadish Kumar, Assistant Professor in CK College of Engineering and Technology, Kadalur. So thank you, sir, once again for your wonderful lecture, and thank you to
everyone everybody
for the presentation. Thank you.
Thank you, Guts. Thank you.
Yes, sir. Wait. Still, what of thanks is there?
Thank you very much, Dr.
Hello,
Suresh.
sir. Thank you, Dr. Kumaresan, for announcing the election formalities as well as announcing the next week's program. Now I call upon Dr. Raju, Honorary Secretary, Indian Valley Society Southern Zone, for proposing vote of thanks.
One more announcement.
Raju, please wait. Chairman on top.
Okay.
Please, sir.
One more announcement.
Yes,
now, for the chairman-elect is available. Let us congratulate Engineer Rajasekhar. So he will be taking that next session.
Congratulations, Rajasekhar.
Thank you, sir.
Congrats,
Thank you, sir.
Congrats.
Thank you, sir. Thank you very much.
Thank you. Yeah, now we can proceed.
Raju, go ahead.
Okay. That was an excellent presentation by Dr. Suresh on a prestigious Government of India project. He has not only exhibited his technical knowledge, but also his presentation skill. In fact, I was one of the beneficiaries of Dr. Suresh, and I had the opportunity of working under him when he was in WRI and took his guidance a lot, particularly in the field of distortion control and stress analysis. I also visited this site along with him in the very preliminary stage of trial assembly. Further, I couldn't make subsequent visits due to delay in execution. And I'm glad to share with you that we together carried out many consultancy projects when we were in WRI. A highly knowledgeable personality in welding, particularly in the field of distortion control, stress analysis, and heat treatment of welds. Thank you, Dr. Suresh, sir, for sharing your knowledge.
Thank you. Thank you, Raju. How are you?
Fine, sir. Very fine. And I also thank each attendee of this webinar who are benefited by the knowledge of Dr. Suresh, sir, and interacted with the speaker. I look forward, all of you, to meet you again in a similar occasion. Goodbye and take care.
Thank you. Good night, one and all.
Good night.
Good night. Good night.
Bye. See you. Bye. See you.
Thank you all. Take care.
Thank you.
Yeah, Engineer Rajasekhar, you can end the meeting now.
Okay, sir. Thank you. We will end the meeting now with the permission of everybody. Thank you.